voltage, what will happen? So the mu, that means the chemical potential of one will go higher and the chemical potential of the other will go lower, but and then on the side. But due to their high density of states, the electronic level will not change. It is similar to the fact that suppose you have two buckets of water, and if you take the water from one bucket to another bucket 100 ml, the water level will not change. This is like a classical capacitor. Okay, only the height of the bucket matters. But in the case of graphene, it is one side, the density of states is low, so it is equivalent to, you can think of that one side, the graphene side is just a measuring cylinder, and the metal is just like a water bucket. So if you take 50 ml of water from the bucket and give the same amount to the cylinder, the water level in the cylinder will change a lot. So it is related to the fact that the density of states of the graphene is low near to the Dirac point, and this gives rise to the change of its intrinsic chemical potential. So these are the unique properties people applied in different areas of applications. Here I have listed some of the applications like solar cell, batteries, supercapacitors, high speed transistors, and EMI shielding, and automatic automobile, airplane components. So a lot of, I mean, you cannot right now find any field which has not been touched by graphene. So in any field, the bioimaging, in every field, graphene is there. Here I would like to emphasize on some energy storage measures first, because this is the topic I have done my research most. So why the energy storage? Because you see that people are right now trying to go for the green energy, the renewable energy, solar energy and wind, but those energy are intermittent in nature. You cannot blow the wind on demand, and sun is not there in the night. So you have to store the energy. That means all those renewable technology must have some energy backup. You need some energy storage device, the battery or supercapacitor. Similarly, I think right now you are also using everyone is using either mobile or the laptops, and for it requires some battery. That means you need to have a portable energy storage devices. And next generation cars are also electric vehicle cars. And for that, graphene is a good or excellent material for the energy storage. And I'm talking about electrochemical energy storage, where the energy stored due to the storing of charges on the surface of the graphene. Now, if, as I already mentioned, that graphene has a huge specific surface area, so if you can store your ions on the surface of the graphenes, individual surface of the graphenes, you can store huge energy within the same amount, suppose 1 gram of graphene. So, but there is a real issue. The issue is that because the graphenes are two-dimensional sheets, they have also strong interaction to restack back in terms of the graphite. Because people can make the graphene from the graphite, but the graphene again, they have a tendency to restack again to go to the graphite phase. And if they restack, then what happens that you cannot access the intermediate layer. You can just access the outer layers only. So how to restrict those restacking problem, which is a huge problem for graphene-based system in energy storage? There are different strategies. I have actually adopted some strategy which is known as the graphene gelation, and I started with some micron-sized sheets of graphene, which is dispersed in water, and by some simple methodology, I made them assemble on the interface. And when they assemble on the interface, metal interface, and the water remains intercalated between the graphene sheets, so that I can reduce the restacking of the graphenes. And this particular material is very similar to the gel. Gel people use, you know that the contact lens is also a kind of gel. So similar kind of gel we have prepared from graphene, and this is very simple. We started with some metal plate, this just dipped into the dispersion of graphene oxides, And if you want to know the very detail, you just follow the our this 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 reference which we have published here, and you can see from this image, ACM image, where this is written as 5 micron, you can see that the individual graphene sheet, there are many pores in between. That means there is no complete restacking of the graphene. By this strategy, we can actually reduce their restacking, and we can of course control the orientation of the sheets by some tuning the dilation conditions, and uh, and then we used it for the supercapacitive energy storage, and we have found that it is actually it can be charged and discharged at a very fast rate. Within some millisecond scale, you can charge it. And the aerial capacitance is also very good. And this is, and the increase of current density, you see that the 150, this is the, at this rate, if we can charge or discharge, still it maintains a good capacitance. So it means that this is good for ultra fast charging of the capacitors. These are some metrics we have compared with the very excellent other papers. And there is a modern flexibility demand as well, because the electronic components, they are going to be more flexible. You can find the flexible display, all that. But for all those electronics, you need to have some power backup. But most of the power backups are rigid one. The battery is rigid, battery is not flexible. How to make it the flexible energy storage devices? We have used the same for flexible energy storage devices. And this undistorted curve at bending at different angles also shows that we can use this as an energy storage device which is bendable, and bending does not cause any harm to the performance. And next, I am going to just present a interesting topic, that how to tune the electronic properties of graphene. So graphene is made up of carbons, but if you replace carbon with some other heteroatoms like nitrogen, sulfur, phosphorus, so that you can change the electronic property locally. And depending on their dopant site, where the individual atoms are, the dopant atoms are, they have a different arrangement. You can see that here my atoms is there, it is connected with 2 carbon atoms only. But if it is here, it is connected with 3 carbon atoms. This is known as the graphitic nitrogen, whereas here this is known as the pyridinic nitrogen. And if it is connected with the 5-member cycle, it is known as the pyrolytic nitrogen. So depending on the different configurations, their electronic properties are also different. And but suppose this is, I have given the example on the basis of the nitrogen. But what will happen if you want to incorporate some elements which has a large atomic radius, like sulfur? If you want to incorporate it, so what will happen? Due to its very large size, it is hard to incorporate within the lattice site, because it will create a lot of strain, so it is impossible to. But you can see that at the edges where there is some defects, if we have some pores or defects, here even if this atom has a larger size, there is no issue. So we took this as a some kind of theory. If we can create some pores, we can incorporate some big heteroatoms. But how to create the pores within a graphene? So we started with graphene oxide, and graphene oxide, as I mentioned, this is a functionalized form of graphene. But then there were already reports that in a graphene oxide there are some patches, a region where there is no functionalization. This is graphene-like, and there is also some patch here. This is functionalized. So this is a percolated network of graphene and functionalized graphene. Now we took this as in some information, important information, that because it has a 2 percolated region, so if we heat it, the graphene oxide, then we can expect the 2 different regions due to their 2 different chemical structures. They have a 2 different burning points. So we control some temperature, 440 degrees Celsius, and found that those functionalized regions, those are most disordered region, they burn first. As a result, we can create some holes. These are the holes and very tiny holes we can create. And once we create the holes, now it is easy to dope with the bigger heteroatoms. We have doped with the sulfur, and those sulfurs are mostly incorporated near to these pores because they are because we have confirmed it from the XPS that the configurations of these sulfurs. And we have done also density functional theory simulation. From that, we have found that due to this heteroatom doping, there is a redistribution of electron and the spin around some atoms around the edges. So this redistribution, localization of electrons has some impact on the catalysis. We used it for the oxygen reduction reaction catalysis. If you would like to have the more detail, please go to this publication. And with the same, we started another strategy where how can the dopant site graphite like this?
Sir, sorry for the interruption. Actually, I'm sorry to say that we are running short of time. So
Okay.
Next 2 minutes, sir.
Okay. So here we have actually we did some dopant specific unzipping. This is a carbon nanotubes. When it is unzipped, it gives rise to the nano ribbons of graphene, and this is the specific process by which we have done it so that it remains crystalline in nature. So it is very different from the other reported methods. There is a lot of disorder. You can see that from the TM image, the crystallinity atom there. From this atomic resolution image, we have also confirmed that crystallinity is there. And from this XPS spectra, we have also seen that the unzipping happens mainly started from this pyridinic nitrogen. So that in the XPS after the unzipping, there is no pyridinic peak. And this is the mechanism of, I'm not going to detail of this mechanism of unzipping. And we have also done the doping of the graphene, where because it is a surface only material, anything put on the graphene, it can change its electronic properties. We have actually given the 2 different polymers in the 2 different regions, junction diode, and there are, because from the success of the graphene, people have started with exploring other 2D materials which are analogous to graphene. They have different properties. Here there is some list of some 2D materials: graphene, boron-nitride, silicene, and molybdenum disulfide. Particularly out of these, this is actually currently dominating the field, which is known as the magazine. It's a delaminated titanium aluminum carbide. This is also 2D materials, but it is conducting. You can think of it as a conducting metallic sheet floating within the water. And this is the monolayer of MOS2, where you can see that in the bulk phase it is a indirect band gap semiconductor, but in the case of when it turns into the monolayer, this is a single layer, it's changed into the direct band gap semiconductor due to there is a removal of the interlayer coupling. With this, I would like to thank, and this is my mail ID. If you have any question, you can drop me a mail. Thank you very much.
Let's all thank Dr. Maiti for such an interactive session, such a nice session. We have time for maximum 1 or 2 questions. If anyone wants to ask, please ask, because we are running short of time. We have to carry on. Those who want to interact with him personally, please follow his email ID. If there is no questions, let's thank Dr. Maiti once again for such an interactive talk. Sir, you have to
thank you very much.
Presentation mode. Yeah. Thank you so much, sir. So now I'll go to the last invited talk for today. And the talk will be presented by, again, a friend of mine, Dr. Narajole Raj, who is currently a research fellow in the Center of Advanced 2D Materials, located in the National University of Singapore, NUS in Singapore. Narajole Raj has done his MSc, particularly integrated PhD in Indian Institute of Science, IISc Bangalore, followed by a 6 year of PhD. After that, He has been a research associate in again in Indian Institute of Science in Bangalore. Oliver has published 6 research journals, very prestigious journals like Advanced Materials, Nature Nanotechnology. There also has been work experience in Western Digital Bangalore R&D jobs. So with this, let's welcome Dr. Oliver Rai, and he will be talking about photons, plasmons, and nanometer size gaps. Paulol, over to you. You can unmute yourself and start presenting.
Hi, am I audible, operative?
Yes, yes, absolutely, Paulol.
Okay, I'm just. I believe the screen is visible.
Yeah, it's coming. Yes, Paulol. Make it full screen. Yes, yes, yes. Make it full screen. Yes, yes, perfect.
Okay, thanks, Operative, and thanks, Professor Tapanendo Kamlia and other organizers for inviting me into this seminar. I'll be talking about photons and plasmons in nanometer size gaps. Basically, I mean, by now, I believe it's clear that nanometers of our various various interesting physical phenomena. And also it offers to control various physical parameters. That's why these are interesting. In the context of photon and plasmons, I would also like to, in the context of photon and plasmons, I'd like to show that how nanometer size gaps can offer interesting stuffs. These are the outline of my talk. So first I'll talk about the motivation, like why these kind of studies are important, and then basic physics and like which is very much metal permittivity, and then there will be few nanoscale devices, specific nanoscale devices, where will show that how photon and plasmonic responses are controlled, and then some examples of applications will be shown, and then at the end, just with only with very few slides, I would like to show what we are doing in this field in our group in NUS. So that is this part, which is electrically controlled on-chip plasmon emissions and detection. That is the last few slides. Otherwise, it's a general talk in terms of photons and plasmons in nanometer size gaps. So motivation. So let's see what is light and what are plasmons. So light is basically electromagnetic wave. It's an which oscillates at very high frequency. We call it optical frequency. And whereas plasmons are basically dielectric. Plasmons are basically oscillation of free charges in metal, and it can occur inside the bulk of a metal, but the most interesting part is when it occurs at the interface of a metal dielectric. So this is the main part of it that I'll be talking about. And one interesting uh, uh, thing that I should point out is, so when we are talking about plasmons and metal dielectric interface, then the electric field in the Z direction basically changes. How it changes in the Z direction, it's shown in this graph, where you can see that on the upper side of the metal plane, it extends around, say, 100 nanometer length scale, whereas inside the metal, it extends around, say, 10 nanometer um, uh, uh, 10 nanometer region. And so these length scale, I'm catching your attention by these red arrows. are important because these are the lens scales which basically tells us that nanomaterials can be interesting because electric field will interact only in this length scale if we are interested inside metal or outside metal dielectric interface. And these are few example of a different type of metal dielectric structures. You see that this is metal dielectric single interface, whereas there are like two interfaces. Whereas this yellow is basically the metal, and this light green shade is basically dielectric. And then various types of devices are realized just to facilitate these fundamental like just to optimize this, just to facilitate light matter interactions by controlling these length scales, keeping these length scale in mind. And one more quick thing is basically I should also point out is light and plasmons are completely different in terms of as far as the nature of energy are concerned. So light is, as I already mentioned, it's electromagnetic wave, whereas plasmons are electromagnetic waves inside a metal. So the dispersion relations are different. So in principle, from light to plasmon, one has to go via some change, go via changing momentum vector. So in short, if we summarize, what are the advantages and disadvantages? So light, photons basically offer diffraction limit. Photons are diffraction limited, whereas plasmons can go beyond diffraction limit. Photons are low loss things, whereas high loss happens in plasmons. Low interaction generally are observed in photons, whereas in plasmons, strong interactions are observed. So, and in terms of in terms of devices which are operating at optical frequencies, so these are the kind of a chart where you can see the dimensions versus the speed has a connection. So photonics offer high speed, but at larger dimensions, whereas if we go to the nanometer scale dimensions, then we can have similar speed, but with plasmonic materials. So just to go to now to the basic part, basic part, how the metal permittivity offers plasmonic response. Basically, what I'm just showing here is basically light is an electromagnetic wave, which I already told, and then it interacts with free electrons, which undergo simple harmonic motion, and then free electrons with no damping loss basically gives rise to negative but real permittivity. So whereas free electrons with damping loss gives complex permittivity. So these are the two important parameters: negative permittivity and complex permittivity, which are tuned via various types of devices. And basically, that is again reflected in this dispersion curve, where you can see that plasmons basically without loss, it basically follow a certain energy momentum relationship, whereas which is like curved, whereas photon is a straight line. And this comes from very simple understanding of Drude model, where you can basically if you write down the force equation, where electrons are placed inside an electromagnetic wave, it basically gives rise to this complex permittivity. So that is what I'm telling is important. If you want more information for the students, you can follow this book, which talks about the detailed evolution of this theory of metal dielectric theory. And basically, I mean, whereas here I'll be talking about more about the consequences of these complex. My laptop is stuck. So consequence-wise, when I'm coming again to the dispersion relation, so what you can see is basically, let's talk about, say, metal air interface, the dispersion relation. Then what you can see is the same energy actually can have a different set of wave vectors, which is very large in value compared to the wave vector which light can offer. So this basically tells us that the wavelength of a plasmon can be very smaller in size, and hence it can be squeezed basically beyond the diffraction limit. So that is the beyond diffraction limit. That is one of the most important conclusion of metal dielectrics, of the property of metals, which are used again and again in plasmons. Now, if I go quickly, if I show quickly what is, so as I was telling, is basically metal plasmons and lights are fundamentally different. So in principle, there are two different forms of energy. So you can't, so you have to go via a certain mechanism to go from one form of energy to the other. And this is basically shows one example of how they are excited. For example, say if we want to excite plasmons which are occurring at this metal dielectric interface, this part of the metal dielectric interface, which is coming over here, then we have to shine a light in a certain angle, which will connect via this metal thickness and excite this plasmon. So this is a momentum match phenomena, which are demonstrated over here, and definitely depends on the thickness of the metal. So if we, that is because of this this part of the electric field we are utilizing, and if it is too thick, then we'll not be able to excite the plasmons which are occurring in this thickness. So I'm just again talking about the basic nanoscale idea, like why nanoscale systems are important in terms of plasmons. Anyway, there are multiple such structures which can be used to excite plasmons, and it's not just a prism. It can be grating. It can be many other system like a scatterer, which and that also gives moment idea. So let's look at now few like control via specific device design in nanoscale. So this is one of the famous metal dielectric system which shows that the effective index can be controlled, and hence so for example, you see there is a dielectric dielectric rod which has a dimension of d, and then it is placed on top of metal by a gap of certain height, by a small gap which is filled by another dielectric, and then the effective index of this system, you can say you can relate to the permittivity also by effective index changes as you change the gap. Say, for example, here it's tuned from 2 nanometer to 100 nanometer, and hence effective index changes drastically. And what is the consequence of this index change? You can see it over here. It's basically, if you look at the bottom images, then at when the dielectric cylinder is placed much above the metal, then all the lights are inside the dielectric, whereas the moment you are placing it near the metal, and basically light is interacting with the metal and getting focused. And you can see here also, here in this image, light is mostly residing inside metal dielectric interface, and that is basically, this phenomena is represented by the mode area, which is basically effective area within which most of the energy is confined. And you can see the effective area, mode area, which is normalized by the area when it is not interacting with the metal plate, it can be like 100 times smaller when these dielectric and metals are placed only a small nanometer, few nanometer apart. And definitely it has a consequence. Is basically, although the light is getting confined in metal dielectric interface, there is a loss that has to that comes, and because of that, so you can see the propagation loss. So for example, is high. For example, if we take any particular D, say 500 nanometer, then we compare it with different gap size of different age, say for 100 nanometer gap versus 2 nanometer gap, then you can see that the propagation length is very different. It changes by almost 2 orders of magnitude. And so another example of such confinement, light confinement, is basically you can see you can achieve in metal interface. You can see in this graph is when there is a small. So in this graph illustrates different mode energy, plasma mode energy at a different gap size. So this is again, I should mention, previous one was metal dielectric interface, whereas this one is metal interface, which are placed at a small distance. Say for example, this one is 3 nanometer gap is there, whereas 30 nanometer and so on. And you can see the effective mode energy you can which is presented over here are changing. As we change the gap, as we make the gap smaller, resonance energy is increasing. So this is also another phenomena which is a consequence of light matter interaction at smaller gaps. This is another beautiful example where one can show that two metal nano structures which are bow tie in nature, that when they're placed one in front of the other, so electric field enhancement happens, and that gives rise to a physical phenomena which is the study of Rabi splitting. So Rabi splitting is nothing but energy exchange between two different state of matter, two different state of systems. So in this case, what is happening is, in this metal dielectric, in this metal interface, which is storing one form of energy, and that is interacting with nanoparticles which are placed inside these gaps. And so that changes the scattering phenomena of light, and that is observed. You can see there is a deep scattering is less when the interaction is strong between the cavity and these nano dots. So this splitting is called the Rabi splitting. This is one interesting physical phenomena and very fundamental in many cases. Another metal interface, metal insulator metal structure, which gives rise to a different form of physical phenomena, which is light emission. So generally, light emission from a semiconductor is known, that is via spontaneous emission, jump from higher energy state to the lower energy state of matters. So in this case, what is happening is basically electrons are tunneling from via inelastic method, and hence giving rise to emitting a light is called inelastic tunneling phenomena, and that can also act as a light source. So you can see that density of states are very high when two metals are with sharp interface are placed very small distance apart, which is of the order of few nanometer only, 1 or 2 nanometer only. And quantum efficiency is getting higher, which is of the order of 1%, as also the dimension in the Z direction, which is the thickness of the cube, is changed. Um, so I'll quickly show a few more examples in this context. So usefulness of this light matter interaction phenomena, which is a laser. So what happens in this case is a silver surface, and and another semiconductor is placed with a small gap of dielectric. So this is a metal dielectric interface with a small gap, and then a mode confinement happens in the metal dielectric interface, because of which light amplification occurs. So you can see within the plane of the structure, light goes full internal reflection, total internal reflection, and facilitates lasing. Again, nanostructure plays another. So the lateral dimension of this device also play an important role, because you can see when the structure is changed from square dimension to a irregular dimension, the number of modes can be controlled. In this case, on the left side, we can see multiple peaks, which is controlled by the dimension of the structure. Another classical example in the photonics, where light is coupled via grating into a plasmon, and then it is again taken out after some modulation. This is high-speed plasmonic modulator, which operates at very high speed, gigahertz, gigabyte speed. So what is happening, you can see, is basically light is coupled on the leftmost side, and it has mostly this type of nature as it and then it starts interacting with the gap, and then that is where modulation is, and ultimately it is taken out by the scatter by the so another interesting physical phenomena is squeezing light at very small gap, which facilitates mixing of frequency and photo generation. So photo mixing, which is a nonlinear phenomena that happens because light is squeezed so much that the electric field is now very intense, and hence simple harmonic motion of electron cannot be assumed any longer. So light now interacts non-linearly.
Sorry for the interruptions. Actually, we are running short of time, and 3 more talks are coming up. So you have to wrap it up by next 2 minutes. Sorry.
Sure. No problem. This is another example where you can show the switch formed by light matter interaction. There are basically you can see, so there are 2 waveguides side by side placed, and then when a bias is applied, electrical bias is applied, then what happens, the effective index on the left waveguide can be different than the effective index on the right waveguide. You can see that effective index is low compared to the right waveguide, and hence the amount of energy that can be here is different, and hence you can control the path of light that it takes on the left side or on the right side. So you can see that no voltage applied. They have similar intensity on both sides. So light input is over here, light output is here. You apply a voltage, negative voltage, you can see the light is going only on the upper part, whereas you apply positive voltage, light is going only at the lower part. And finally, I'll quickly show what we are doing in Universe here. It's basically, it's a inelastic tunneling, which I mentioned earlier. It's basically, again, when light is coming from one electrode to the other by a small gap, then light can come out. Or another phenomenon phenomena can also happen is basically it can excite a plus one as well. So we take this and then inside a metal MIM structure, density of states can be very high, and using this idea, we have finite plasmonic excitation. And this is one typical example where you can see that it's a gold electrode and then aluminum electrode, which are separated only by 2 nanometer, and then inelastic tunnel happens, and then that excites plasmons. And then the similar phenomena can also help in detecting the plasmon. So it's basically in one side you have plasmon source, on the other side you have plasmon detector. So the advantage of this is basically this is happening via tunneling, and hence it can be very high, it can operate at very high speed. This is basically the detection phenomena. On the left side is a modulation at the voltage input, and on the right side the detected voltage output. And we also understand the mechanism by which this kind of excitation is happening. Is basically we generate via MIM gap, and then that goes to surface plasmon via various pathways. And we control that. For example, in this phenomena, in this presentation, what we're showing is if we control the gold thickness, aluminum thickness, then so in one case we have a small aluminum thickness, and hence we have a specific type of SPP, whereas it's a specific type of SPP which is occurring at aluminum glass interface. And if we increase the thickness, then that surface plasmon is completely gone if we have larger aluminum thickness, which I mentioned earlier. So with all these, I'd like to thank you for your attention. And in terms of conclusion, so this is I already mentioned, and thanks for your attention.
Let's all thank Dr. Kallol Roy for his wonderful interactive session. Unfortunately, we don't have any time for interaction, so the audience, I would like to request you to contact Dr. Kallol Roy in his email ID personally if you have any questions regarding his presentations. Thank you, Kallol, for your wonderful talk.
Thanks, Sabrodev.
Now, with this, our invited talks for today is concluded. So now this is time to carry on, and we'll go into the paper presentations. We have three paper presentations today. I would like to request the paper presenters to finish their presentations within 10 minutes because we are running really short of time. So our first talk will be given by Dr. Piyush Kanti Samanto from Kondai Prabhat Kumar College, and he is going to talk about electrical and optoelectronic properties of chemically synthesized zinc oxide nanoparticles. Dr. Samanto, you can unmute yourself and start your presentation.
Okay. Thank you, Dr. Pradeep, for giving me, and also the organizers for giving me the opportunity. And am I audible? Am I audible?
Yeah, yes, sir. Absolutely fine. You can start your presentation, sir.
Okay. So, what I'm going? Is the PowerPoint is visible now?
Yes, sir. It's absolutely.
Okay. So I'll just discuss here in short the electrical and optoelectronic properties of zinc oxide nanostructure synthesized by a chemical route. I'm skipping these introductory parts. And as we know, it is a very popular material, zinc oxide, basically a 2,6 type semiconductors with high band gap, and the band gap is direct band gap, and it exhibits high transparency to visible window. It has an excellent piezoelectric property that can be used for green energy harvesting, and excellent luminescence property that may have potential applications in electronics and several biomedical devices. So with this brief introduction, I'm starting my lecture, and I'm skipping the chemical synthesis part because this is a very standard protocol and that are available in literature. In brief, we have just used zinc acetate and lithium hydroxide, and by appropriate stoichiometric ratio, we followed the standard protocol for the chemical method and prepared the materials. I'm directly going into the results. The structural studies involved the extra diffraction studies, and here it shows the X-ray diffraction pattern of the synthesized material. Sharp peaks appeared over here that indicates the well crystallinity of the material, and we have indexed these peaks with and found the structure to be hexagonal, and these peaks indexing is quite consistent with the standard JCPDS. And from the diffraction curve, we can also calculate the crystallite size. In fact, by crystallite size, we mean here the coherent domain participating in diffraction of X-ray. And we used a Scherer formula to calculate the particle size, where this beta is the full width at hub maxima of the peaks and theta is the corresponding diffraction angle. And we considered the highest intensity peak for this calculation. This calculation shows that the crystallite size is 16 nanometer, which is very small. And we also see that the intensity of these different diffraction peaks are different, which clearly indicates that the growth rates of various facets of the zinc oxide crystal is different. So we have studied here the degree of orientation, which basically the fractional intensity of a particular peak to the aggregated intensity of all the diffraction peaks, which shows these green bars are the observed data and the blue bars, and the green bar shows the standard JCPD results. The results are almost consistent except this 101 peak, that is due to the difference in the surface energy of this phase as per the reported structure. We also studied the impedance spectroscopy to study the different contribution of grains, grain boundaries, and electroelectrolyte interface effects on the impedance of the material. So this graph shows the frequency dependence of both the real and imaginary part of the impedance. And these formulas are well established, so I am not going into details. And, and this figure shows that both this real and imaginary impedance gradually decreases with increasing frequency. So as we know, as we increase the frequency, obviously the space charge increases, which in turn reduces these impedances. It is also observed that the imaginary part of the impedance has a higher value compared to this real part. To understand the various contributions like grains, grain boundaries, and interface into the impedance spectrum, we use the Nyquist plot where we have plotted the real part of Z and negative imaginary part of Z. We get a pattern sort of like this. So this pattern can be divided into two parts. One is this semicircular arc, and this is a larger arc. So the first part is responsible for the bulk contribution, and second part is for grain boundary. And we see that this arc is quite large. This indicates that the grain boundary has a large contribution in the electrical conductivity of this material. And from this semicircular arc, we can find the bulk resistance of the material. That is from the bulk contribution. That was about 160 kilo ohm. And ideally, this circle it should be ideal circle, the centered at this zero axis. But we see a depression of the curve due to non-divide type of relaxation procedure that can be incorporated by using additional constant phase element into the equivalent RC network of the dielectric system. So this figure shows the variation of the conductivity, AC conductivity with frequency. A plateau is observed in this low frequency region. It indicates that in the low frequency, the conductivity is almost frequency independent. But as the frequency increases around 10 to the power 4 onwards, then the conductivity goes on increasing. And beyond a certain characteristics frequency, again, it shows a saturated or lower behavior. And the DC conductivity can be calculated from these intercepts, and it was calculated to be 4.9 10 per -8 ohm centimeter inverse. To study the relaxation phenomena, we show here the loss tangent spectrum as a function of frequency, which shows an initial increase of the loss tangent to critical values up to 2.75 kilohertz, and it gradually decreases for higher frequencies. This is because, as we know from the theory of dielectric polarization, that on application of an alternating electric field in dielectric sample, the dipole tends to oscillate with the frequency of the applied field. But beyond a certain frequency, the dipoles may no longer be able to follow the oscillations of the electric field, and the oscillations of the dipoles becomes out of phase and leading to the dissipations of energy. So this is how the energy dissipation occurs. And the relaxation time we found is quite low. This is 0.36 millisecond in case of our samples. And this was calculated from this graph. And this decrease in the higher frequency region may be attributed to the accumulation of space charge due to in the high frequency region. The optical properties of the material were studied by observing UV visible absorption spectrum and photoluminescence spectrum. This graph shows the UV absorption spectrum of the sample, which shows the low absorption property of the material. That means the material is quite transparent, especially in the visible window. And we can use tau equation to calculate the band gap from this UV visible data, where this alpha is the absorption coefficient and H is the band gap of the material. And for direct band gap, this exponent is half, that is here it is 2, and for indirect band gap this will be half. So as you know, the zinc oxide is a direct band gap semiconductor. We have used this equation, and getting the slope from the high absorption range, we can calculate the band gap to be around 3.52 electron volt. So this is the photoluminescence spectrum of the sample, which shows a strong photoluminescence peaked at around 582 nanometer. So usually, as zinc oxide has very high band gap, the visible emission, UV emission is the characteristics emission because of this high band gap, but it shows visible emission due to the presence of defects that may grow during the low temperature chemical growth. So here we see the emission peak, it shifts towards this towards 582 nanometer, and as there is no doping, so it is obviously due to the shallow level emission, that means due to defect states. And the defects energy states has been already calculated by many researchers, and from their data we can see that this emission can be correlated to the existence of some interstitial oxygens in the synthesized zinc oxide crystals. So in conclusion, we have successfully synthesized well crystalline zinc oxide nanostructures of woodite crystal with size 16 nanometer. It exhibit a non-Debye type relaxation process which induces an additional phase in the equivalent RC network of the equivalent dielectric model. And we observe a large grain boundary effects because since the materials is nanoresin, so lots of grains are created. So grain boundary effect is quite high as it is expected, and loss tangent increases in the high frequency region due to space charge accumulation. And I have already mentioned that this optical emission is due to the oxygen interstitial. So here I end up my lecture, and I must acknowledge our college and the DSTP government of India for providing these measurement facilities in our lab. So thank you very much.
Thank you, Dr. Samanto, for such a wonderful talk and your insights on the novel characteristics of the zinc oxide nanoparticles. Let's carry on. Our next talk will be from the southern part of India, and it's the talk by Dr. M. Krishnaveni from Manonmaniyan Sundaran University, Tirunelveli, Tamil Nadu. So I would request Dr. Krishnaveni to start your presentation and to unmute yourself. Ma'am, are you online?
Sir,
please repeat the name.
hello, sir.
M. Krishnaveni. Yeah. Ma'am, you can start your presentation.
Yes. Thank you for giving an opportunity to present my work here. So I'm very thankful to organizers. I'm going to present my presentation on structural and textural characteristics of a nanoporous material and its catalytic application. Sir, my PPT is not supporting.
Now,
Hello,
are you
sir.
presenting in smartphone or you are in laptop?
Sir, I'm in mobile phone. I'm presenting.
Okay, you will be able to see there is a button called present now, and from there you will be able
Actually,
to.
PPT is not supporting to me.
Okay, actually we don't have much time, so at least you can, if you don't have the PPT, you can't open it. You just briefly tell us about your novel work, about your.
Okay. Thank you so much.
Yeah.
Yes. So today I'm going to discuss about structural and textural characteristics of nanoporous aluminophosphate and its catalytic application. So in the investigation of the synthesis of aluminophosphate molecular sieve from simple method in presence of a low cost effect N-butylamine as template without autoclave. Generally most of the catalysts are synthesized by the help of autoclave. For that we have to need a large amount of pressure and temperature. But in our method, there is no need to use autoclave like that. By the simple method, we synthesized aluminophosphate molecular sieve using an amine template. These catalysts, it is characterized by various spectroscopical techniques like XRD, IR, and surface area beta adsorption isotherm, and SEM, TGA, and TTG, etc. First, the characterization, it is XRD measurements. This indicates the molecule, the peak, it will be appeared in a low angle around 0.6 and 0.5 degree. This indicates our molecules to be crystalline nature of the material. The intensity of the peak indicates the molecule, the catalyst to be crystalline nature. And next, formation of a tetrahedral framework of mesoporous aluminosilicates. Then the thermal analysis, that is TGA. While taking this TGA, there are three weight laws occur for this catalyst. The first weight laws around 100 to 120 degree. This indicates the loss of water molecule. And the next weight laws around 270 degree and 330 degree. This indicates the loss of organic template molecule. After that, there is no weight loss up to 800 degree there, so that indicates the molecules should be stable. The beta adsorption isotherm indicates the molecule to be nanoporous in nature. Because the surface area for alpo is 90.986 and zinc alpo is 248.812. So both the molecules have the pore diameter is around 52 Armstrong and 55 Armstrong. This confirms our molecule to be nanoporous in nature. Nanoporosity of a molecule is confirmed in this method. And the scanning electron microscopy indicates our material, synthesized material, should be a crystalline nature, and the pores of molecular sieves, it is very seen. It seems to be the crystallinity of the molecule. And the EDX also confirmed by the presence of synthesized molecule composition aluminophosphate. And after that, the materials are synthesized and characterized. The characterization confirms the activity of the material. After that, the catalytic activity of the material is confirmed by the use of trans-esterification reaction. In this reaction, the synthesized material is used as a catalyst. We took used palm oil and ethanol. After that, the catalyst. So the trans-esterification reaction has taken place. Important parameters are fixed, that is reaction temperature, contact time, molar ratio, and catalyst dosage. After that, it is optimized. Our catalyst is around 50 degree and 2 hours, 1:3 molar ratio, 0.5 gram catalyst dosage. We could have a good biodiesel selectivity, that is nearly a 92.5% percentage for alpo and 70% for alpo. So this indicates that our catalyst is to be very efficient for the synthesis of biodiesel from waste cooking oil, that is waste palm oil. So this is our uniqueness of the work. Even a 0.5 gram of catalyst dosage, we can synthesize from a waste oil into biodiesel. So the present strategy could potentially contribute to saving energy and time in catalyst. And hold a significant promise for biodiesel production from used palm oil or used cooking oil. Thank you. Thank you for your patient listening.
Thank you, ma'am. Let's all thank
Thank-
Dr. M. Krishnaveni from
Thank you,
Tirunelveli,
sir.
Tamil Nadu. So we have the last talk for today, and it's the talk again on zinc oxide nanoparticle. So let's please welcome all Dr. Vidyut Haldar from Damdam Motichil College, and he will be talking about on positron annihilation studies on copper doped zinc oxide nanoparticles. So Dr. Haldar, you can unmute yourself and you can start your presentation. If you find any difficulty, please let us know.
Well, can you listen to me?
Yes, sir, we can listen to you, sir.
Can you see the slides?
Not yet, sir. You have to go to the right side at the bottom, present now button. You have to click
That
it.
I've done, and we have done. I've done it. Okay.
Then you just open your presentation. You just at this situation minimize everything and open your presentation.
Okay, I will go to the screen and share. Okay, and then
Yeah, share your window or entire screen, whatever. You click any
Okay.
one of them.
okay.
now
Can
it's
you?
coming. Yeah, it's slowly coming, sir. Yes, sir. Yes,
Okay.
it's coming. Yeah.
So can I start? Okay.
Yes, sir. Sure.
Very good noon to all of you. I am Dr. Vidyut Haldar from Damdam Motichil College, Physics Department. So today I'm going to give a talk before you on the topic positron annihilation studies on copper doped zinc oxide nanoparticles. Okay, our objective was to incorporate defect-induced ferromagnetism in copper doped zinc oxide nanoparticles. And why to choose zinc oxide? Because zinc oxide, along with magnesium oxide, titanium dioxide, they are oxide semiconductors, and it has a very wide band gap. Zinc oxide has potential application in room temperature magnetic semiconductors, optoelectronic material, magneto-optic devices, future generation solar cells, room temperature ferromagnetism, etc. Now, defects plays the most crucial role in magnetic and optical properties of zinc oxide. So, incorporating defects induces ferromagnetism in such system is a topic of intense research nowadays. So, by employing positron annihilation spectroscopy, these defects can be characterized. In our earlier paper, okay, in computational condensed matter, we have done some density functional theory studies on copper doped zinc oxide system in order to understand the changes in the electron property in copper doped zinc oxide. And it has been found that copper atoms, when doped at cation sites, produces a significant magnetic moment, along with half two copper dopants have been doped at different zinc sites by varying the dopant distance. This is all done using density functional theory. And then before you, you have two pictures, two figures. On the left, you have the pure zinc oxide system. You can see the density of state is symmetric, whereas on the right, you have copper doped zinc oxide system where you can see a bit of unsymmetric behavior out there. Okay, so that is exciting. So a brief conclusion that we had from DFT studies that we already did was that the total density of states for undoped zinc oxide matrix is totally symmetric, which suggests that there is equal number of spin up and spin down electrons in the pure zinc oxide system. However, in case of copper doped zinc oxide system, the total density of state is asymmetric that we already had. So partial density of state analysis reveals that 3d orbital of copper give rise to the asymmetry due to the presence of unpaired electron in the system. Ab initio calculation reveals that each copper atom doped at zinc site generates a magnetic moment of about 1 Bohr magnetron in the host matrix. The presence of unpaired electron of copper generates non-zero magnetic moment in the copper doped zinc oxide matrix. The value of the magnetic moment linearly increases with the increase in the doping concentration of copper atom. Thus, copper doping induces defects, thus showing ferromagnetic behavior. It has been observed that the band gap of zinc oxide decreases significantly on doping copper atoms at zinc site, which further decreases with the increase in copper concentration. So with this theoretical calculation behind us, we wanted to correlate with the experimental findings. Okay, and therefore we made some sample preparation by taking appropriate amount of zinc oxide and copper nanopowders to prepare samples of 0%, 2%, 4%, 6% of copper doped zinc oxide by weight and mixing them thoroughly, sintering them, and then using ball mill grinding, we have achieved particle size of about 8 to 10 nanometers. And then we are supposed to characterize the sample. So we did it using X-ray diffraction study done to ensure whether the copper is properly doped at the zinc site in all the samples. UV visible spectra were taken to determine the band gap in our sample. Some positron annihilation measurements were done to study the type of defects and their relative concentration. So this particular study, the third one, is of importance in this particular topic, and it's still on because of the lockdown. We are unable to do more number of measurements. And finally, we intend to do some magnetization studies using SQUID. Now, because our main emphasis is on positron annihilation, so to those who don't know about much about the positron annihilation, I'm just quickly going to tell you that positron, being an antiparticle of electron, annihilates as soon as it comes in contact with the electron, or otherwise it can also form positronium atom, where both the electron and positron, if they are in parallel spin, it is called orthopositronium, and if they are anti-parallel spin, they are called parapositronium. And then this positron atom once again annihilates and give rise to gamma rays. And then different mode of annihilation are there. So free annihilation has a different lifetime from positronium annihilation, and really talk about much. Here, in positron annihilation spectroscopy, basically it involves three different techniques. The positron annihilation lifetime spectroscopy. Third one is angular correlation. Out of these, first two are common. The third one is not as common as that. Okay. So in a positron annihilation lifetime spectroscopy, we take sodium-22 as our positron source, which gives rise, emits positron and has a half-life of 2.6 years. As soon as the positron is emitted, it comes through the excited state of neon, which has a very small lifetime of 3.7 picoseconds. This excited state of neon comes to the ground state of neon by emission of a 1.276 MeV. So this gamma ray, when it is detected, it announces the birth of positron.